Good morning, everyone. Uh, Person online, can you confirm if you can hear me? Can you hear me clearly, right?
Yeah, I can hear you.
Okay, thank you so much for confirming that. Okay, so I want to welcome you to my lecture today. Sorry, that should be June 2024. I still have 2023 in my mind. Sorry. Okay, so today the focus is going to be on assumptions of linear regression. Of course, I told you the other time, statistics is like a story that goes on and on. Before now, we were trying to characterize relationship between two variables, and we actually assume a simple linear regression. Let me tell you this. Um, the difference between um, statistical framework and machine learning framework is in statistics. We normally, if we want to characterize relationship between variables, we normally start with the specification of model. So we have assumptions, okay? So when we specify model and whatever model we specify, okay, because we acknowledge the fact that there's you know uh there's a difference between model and reality, and the difference between model and reality is what we call error. I told you yesterday, and because of that, our model, we're always going to have error, okay, components in our model, okay, and whenever we want to make assumptions will revolve around the error. I'm going to say that again. Whatever assumptions we're going to make about a model will revolve around error. Okay. Now, if I want to know how great is a statistical model, then we need to investigate assumptions underlying the use of the model. And that is the reason why today we're going to focus on the assumptions of linear regression model, because when we're specifying model in statistics, that will come with assumptions. Okay, now the model is going to do a great job if assumptions hold. And today I'm actually going to walk you through what are the assumptions in linear regression model. Okay, so that is what we want to talk about today. So these assumptions are also called conditions. Okay, okay. Now, I'm going to cite an example from politics today. I remember, uh, you know, the other time, I think yesterday, we're trying to characterize relationship between the percentage of votes received by a Republican presidential candidate in 2012 and 2016. In 2012, of course, the candidate was Mitt Romney. Of course, Mitt Romney is, I think it's a sitting senator. Okay. So, and of course, in 2016 was former President Trump. Now, you know what we want to do here. Okay. We actually want to assume a simple linear regression, uh, you know, in order to characterize relationship between the percentage of votes received by a Republican candidate in 2012 and in 2016. So X, S in English alphabet, S come before Y, right? 2012 come before 2016, right? And that was why we denote the votes received in 2012 as S and the one in 2016 as Y. Any question about it? Okay, you understand what we're trying to do, right? Okay, because if we know something, okay, uh, if we have information about what they got in 2012, we can use that information to say something about what they're going to got in 2016. Okay, let me tell you this. Uh, we cannot use 2012 cannot explain everything about 2016. Okay, in statistical, in what we're doing right now, okay, we believe that having information about X, we can only explain something about Y, because there's always going to be a place of unexplained. Does that make sense? Okay. Now, now, if I were to do this, if I want to actually, I want to walk you through an example where since elections, election is involved, then we need observations, okay? Where will the votes come from? Then we're going to consider county in the United States. Does that make sense? Okay, this is a map of the United States, okay? And you know what I want to do is to be able to differentiate. I want to use this to differentiate between population regression and fitted regression. You remember yesterday, I actually walked you through population regression, fitted regression, but you know what? You're going to see the difference between population regression and fitted regression in this election uh, matter. Okay, now I need to see the map of United States in the example. This example, we want to define our population now. Okay, you know, when we have a population, right? Okay, which means all counties outside Alaska. Okay, that is what we mean by population now. Alaska is not included, okay, in this study. I'm just saying in this study. And when I say all counties in the United States outside Alaska, that's a big one. That is virtually all counties in the United States. Okay, and in the year 2012 and 2016. Does that make sense? Okay, now because I have information about virtually all counties in the United States. Of course, I'm going to fit a population regression model, not a fitted. Okay, do you see this guy? Oh, give me 1 second. I'm gonna put a pen on that. Okay, I gave you this yesterday. This is a population regression model. Okay, now why do we want to fit a population regression model? Because the observations that we have is a lot. Okay, and this is like virtually all counties in the United States. Okay, is there any question? Any question? You are good, right? Okay, like make sure you ask question if an area is not clear to you. Okay, let me say this. I've been publishing my recordings. I don't know whether you've been observing that, right? Go to the module. Okay, I put record of a particular lecture and I post my lectures ahead of time. Okay, so that's a population regression model. You know what? Why? You know what that guy is talking about? So that guy is talking about on average. On average means expectation. Okay, on average, the percentage of vote that will be received by by Republican candidate in 2016, you know, why represent 2016, given 2012, given 2012, then will be equal to beta naught plus beta 1s. Of course, I told you what beta naught means represent, what beta naught represent. Okay, that's a regression constant. And of course, the beta 1 is the slope. Okay, if that is taken out, okay, now I want you to see this. You know what I've done here? Okay, all the votes received by candidates in 2012 and in 2016 from virtually all counties in the United States were plotted. You remember I told you if you want to have a sense of what model we're going to specify, you need to generate a scatter plot. The scatter plot is a diagrammatical plotting of y against x, okay? And you can see right now, okay, you can see that because I use virtually all counties in the United States, most of the points are very close to the straight line. You know, when the point of when most of the points are very close to the straight line, that indicates a very strong relationship. Does that make sense? It's only few points that actually deviated away. And you know, based on this line, we got that model. You know what that model means? Okay, you know what this guy means. Okay, that guy means, based on what you see here, we got a beta naught to be 4.424, and we got a beta 1 to be 0.990. Okay, so this is using the virtually vote from all counties in the United States. Okay, now, okay, now, do you know that based on this, okay, I told you the other time, what is the essence of study relationship between variables? The essence of study relationship between variables is just to be able to uh to provide an opportunity to make a prediction. If I have information about one, can I actually say something about the other one? Okay, now because of that, if we have generated a model, that's a model right now. That's a population regression model. Okay, now I can use this population regression model. Okay, I can use it in analysis. I can say, okay, if 50% of the voters in a county voted for a Republican in 2012, what percentage of voters from the county will vote for a Republican in 2016? So what do I want to say? What do I want to do now? Actually have information about 2012, and I want to say something about 2016. Okay, I will be able to say something about 2016 because they got a connection, they got a relationship. If there's no relationship, there's no way I'm going to think about that. It's just like we got maybe in this class, maybe we know two friends that are always they always sit together, and maybe one is not around. If one is not around and maybe he has not been coming for 5 consecutive lectures, what are we going to do? We're going to go to the other one that is coming. Where's your friend? Why? Because they have a connection. That's why we ask the question. You understand what I mean? Okay, now if I want to do that, if I want to answer the question graphically, I'm gonna, when it got 50% voted in 2012, then I can actually trace that up to meet the fitted line. Then I will be able to say, I'll be able to make a prediction about what the percentage of vote is going to be for the 2016. Or better still, I can just plug in wherever I see S in the equation. Can you see the equation? I can plug in 50, which is what I'm doing here. Do you see that? I plug in 50 to represent X. And at the end of the day, do you see what I got? That is 53.924. Now, let me tell you that 53.924 is an average. Okay, it's not an exact value. It's an average. So if I want to interpret that, I'm actually going to say 53.924% of the voters in that county is expected. Expected means average. Does that make sense? Is there any question? Is there any question? Okay, whether in person or online. Okay, you good, right? The person online, you good, right?
Yeah, I'm good.
Oh, okay, thank you so much. Now, that is that. Okay, now, the next thing we want to talk about now is what is y given x equal to 50? Do you know there's a difference between, please, I need you to pay attention. Okay, take a look at this guy and this guy. Give me one second. I think I need to. Okay, so take a look at this guy and this guy. They are not the same. You know why they are not the same? The first one is an average. You see expectation on average, but the second one is not an average. It's a random variable. Okay, you know why? Given x equal to 50, that will depend on a county. When you look at the average one has put into consideration all the counties. Does that make sense? Okay, so this is going to vary. Okay, we're going to talk about that later. Okay, now this is the model. Okay, why is it that we've used most virtually all counties in the United States? Okay, we've established a straight line relationship. But let me tell you this. Why is it that all the point why is it that all the point did not land on the straight line? If all the points land on the straight line, then that would be, we're trying to say our model is perfect. Our model is not perfect. The fact that there's a deviation, the fact that some points scattered away, okay, that is a confirmation that our model does not give an exact characterization of reality. And that was what I said. Look at that. Most observation do not land on the population regression model. We call that errors. You remember when we were talking about population? I told you yesterday the difference between errors and residual. Okay, when you use a population regression model, you're going to be talking about errors. Errors is going to be the distance between the original y and the predicted y. Okay, now now I want us to answer this question now. For those observations not on the regression line, dash of them are close to the regression line. If you take a look at this, most of them are close to the regression line. Okay, then dash of them are far away. It's only few. Do you see few that are far away? Okay, now when most of them are very close to the regression line, that confirms the strength of the relationship to be a very strong one. Does that make sense? Okay, that's what I mean. Okay, now for each observation that we've talked about, okay, this is actually the model assumed because y, okay, is a random variable, which is going to be a combination of a deterministic and a random part. Okay, there's always going to be error. Okay, I told you the other time when we were trying to use a model to depict reality, there's always going to be a gap between model and reality, and that very gap is the error. Okay, if I really want to know how to trust my model, I'm going to say that again. If I really want to investigate whether my model is going to do a great job, then I need to investigate the error. Okay, the more error that I got, then the less, the degree of the reliability of the model. If I want to trust my model more, the error should be very small. Does that make sense? And that is the reason why we're going to make assumptions that will revolve around the error. Okay? We're going to make assumptions. Assumptions in a statistical model revolve around the error time. Okay, that is second now. I now want to walk you through assumptions. Why do we need assumptions? We need assumptions because if we want to if we want to know the validity, how valid is my model? Okay, how can I trust my model? Then we need to see whether conditions or assumptions underlying the use of the model hold. Does that make sense? Okay, and what now? And what are these assumptions? And that is what we want to discuss right now. The assumptions say are conditions. If assumptions are not met, then the model is not going to do a great job. Okay, and let us now see the assumption that I'm going to discuss right now will revolve around the error. Does that make sense? Now let's take a look at assumption. Okay, and look at what I said. Assumptions for linear regression are based on the errors. Do you see that? Assumptions of linear regressions are based on the errors, which means we basically want to see or we basically want to see how error behave. Error should behave well. If error behaves well, we can trust our model. What do I mean when I say error behaves well? Error behaves well when assumption hold. I remember one of resource person under the maybe Department of Disease and Control when he said a model is as good as assumptions. put it into a model. So what make a model to be great is when assumptions hold. Does that make sense? Okay, now, and I said something now. These assumptions affect the properties of the estimator of the intercept and the estimator of the slope. Let me tell you this. Do you know that if I really want to use linear regression, maybe on sample, that I'm going to use a fitted regression model, I need to be able to estimate. I need to estimate my beta naught and my beta 1. Okay. Now, if the assumptions of the error hold, okay, then we expect beta naught and the beta 1 that we estimate to be reliable. Because if you have a wrong estimation for beta naught and beta 1, then the model is not going to do a great job. And that is the reason why we say the assumptions that we talk about right now that revolve around the error time, okay, will affect the validity of the beta naught and the beta 1. Okay, now let's take a look at the assumptions now. You know what I've done? These assumptions can be classified into 4. Whenever you want to assume a linear regression, okay, a straight line relationship for variable for 2 variables, okay. Now these are the assumptions that you must investigate. Okay, assumption number 1 is linearity. What do I mean by linearity? Okay, you are assuming a straight line because you believe the relationship is a straight line. What of if it is not? And that's why we need to investigate that. Okay, linearity means straight line relationship exists. And what is the implication? Please, I need you to pay attention now. I want to explain that. What is the meaning of this? Mathematically speaking, okay, we expect relationship between y and s to be a straight line if the expected value of error equal to 0. What is the meaning? Oh, if the error is the distance between reality and model, on average, that distance should be 0. That's what we mean, on average. What does it mean? Okay, let me explain that now. In the context of the example that I cited right now on politics, we were trying to look at the relationship between the percentage of voters that voted for a Republican candidate in 2012 and in 2016. Okay, now what do we mean when the expected value of error equal to 0? It means, in a model, we only consider the effect of 2016 votes on 2016. We did not consider any other effects. Why is it that we don't consider any other factor? We believe that any other factor that we did not consider as a negligible effect. Negligible effect means on average, effect of other factors is 0. Does that make sense? On average, effects of other factors that we do not include in our model is 0. And that's why we don't include them, because we believe they are not going to be significant. Does that make sense? And that is what we mean by expected value of error equal to 0. Okay, the error that we are talking about, we are actually, even though we call it a gap, it can also be seen as any other factor that could make Republican to have a vote in 2016 other than 2012 that we consider. We only consider 2012 as a factor. Okay, that very year, 2012, is not the only reason why Republican is going to get a vote in 2016. But why is it that we did not consider any other factor? Why do we only consider, the effect of 2012? Because we have a belief that effect of other factor is very, very small. Okay, and on average, we call it 0. Any question on that? Any question? Okay, that's what we mean. So when that happens, then we say there's a linear relationship. Now, The next one is what we call independence. Okay. Now, what do we mean by independence? Okay, take a look at this. You know, uh, if I have 50 count, let's say I got counties. Okay, I got counties, and well, 2016 and 2012 X, right? Across counties. You know why? This is the original why. Okay, when if we're able to obtain our model, we're actually going to get a predicted y, right? Now for each county, we're actually going to have error to be y minus y cap, right? Okay. Now for the first county, the error of the first county will be E1. The error of the second county will be E2 up to that. So the belief is that the error should be independent. You know what I mean by independent? We call something error. They shouldn't, the error of this observation should be independent of the other observation. What we mean, there shouldn't be any connection between the errors. Because if errors have relationship, then it means you can predict errors. Okay, so E1, E2 up to En has to be independent. That's what we mean. Now, the next, and that was why we said they have to be independent of each other. Okay, in statistics, it is a special requirement that errors associated with observations have to be independent. We shouldn't have any reason to predict error of one observation from another observation. Don't forget, we call it errors. They should not be they shouldn't have relationship. That's what we mean. Now the next assumption is what we call normality. Okay, and what do we talk about normality? Because we have so many errors depending on observation, and the errors are not going to be the same, right? The error varies. Okay, the error of one county. Okay, let me be specific. Let's say one of the county is Enepin. Okay, Anoka. Now, if I compute the error for any pin, how do I compute the error for any pin? Is is to subtract what what is the percentage of vote that was received in any pin in 2016? Then what was predicted? What was the vote number, the percentage of vote predicted by the model? When I subtract that, I'm going to get error for any pin county. So I'm actually, when I do the same, I'm going to get errors for all the counties here. Okay. When I get the error for all the county, the errors are not going to be the same, right? The error for NAP may be different. It's going to be different from error for Manoka. Okay. Now, because of the variation, okay, we expect them to follow a probability distribution. I'm going to say that again. Whenever something varies, right, then it's actually going to be distributed probabilistically. Okay, now assumption here is that our error should follow normal distribution. In statistics, we have different kinds of probability distribution. Okay, and of course, because normal distribution has a bear shape. Has anybody seen the shape of a normal before? If you check the material that we review, you're going to see the distribution. It has a bear shape. Because of that, it's very, very useful in statistical analysis. Okay, so we expect errors to follow normal. Okay, in this course, I'm actually going to walk you through how to investigate each of these assumptions. Okay, now the last one, the errors should have equal variance. They should have equal variance. Okay, so, and if I want to summarize all these four, mathematically speaking, I can summarize them to be what I have. Give me 1 second. Okay, so they can be summarized to be this. You know what that guy says? It means error. IID means identically. I know the other I means independent, distributed. Okay, so the errors are independent. They are identical because they follow the same distribution. which is normal. They follow the same probability distribution. And, n means normal. Zero means they have a zero mean. You can say the first one, expected value of error equal to zero. That means the mean of the errors. Okay, they have a zero mean. Then what is sigma square? Sigma square means they have constant variance. If you look at equal variance, the variance of E1, the variance of E2, up to the variance of En, they are all the same. That's what we mean by sigma squared, which is a constant variance. Is there any question here? Go ahead. Oh, visual representation. Exactly. We're doing that in this course. This is just like introducing. Exactly. That's a good question. They all have a visual representation that you said. So, but yeah, just to like tell you, give you information about it. Okay. Now, now, do you know that when the assumptions hold, when the assumptions of linear regression hold, then they all have implications. Okay. Now, implication of each assumption is what I want to figure. I want to tell you right now. Okay. What is implication? If linearity assumption hold, okay. If the linearity assumption hold, then it's indicating that we can use a population regression model. Does that make sense? So its implication is that the expected value of that should be equal to that. Okay. Now, what is implication of independent? Okay. Implication of independent is actually means your response variable is also independent. What is the response variable in this case? What I'm trying to say, when errors are independent, then the response variable is what the candidate got in 2016 at different county are independent. And it shouldn't be that, oh, because Minnesota voted for this candidate, Mississippi is also going to vote for. No. Does that mean saying they are independent? That's what we mean. But before you can have independent or for Y, before Y can be independent, we have different Y, right? Y here is going to be the numbers of the percentage of votes received in each county. Does that make sense? So before they can be independent, the errors have to be independent. Okay? Well, that's a special requirement in statistics. Now, what is the implication of normality? Okay, then the response variable Y also going to be normal. Because you know why? We expect the response variable Y to follow normal distribution. But the only condition under which the response variable Y is going to follow normal distribution is that the errors we need to first follow normal. Does that make sense? We don't just use model in statistics. Every statistical model has assumptions. And let me tell you this. If you ignore assumption and you just use the model, then we're actually going to take a decision that we're going to regret at the end of the day. Okay, what is the essence of using a model? A model that cannot be trusted. And that's why this has to be investigated. What I'm giving you right now, just the implication of the assumptions. Okay, what about for the equivariance? Okay, the implication is that Y given S, we also have equivariance. So you can see the consequence of of violations. If all these are violated, then that will also going to be violated. And if that are violated, you know what is going to happen? You cannot trust your model. And that is the reason why at times it's going to look as if our models are failing us. Our models are not failing us. We are the one that we're not doing the right thing. And how are we going to do the right thing? We make sure we investigate assumptions underlying the use of a model. Does that make sense? Okay. Now, the other time I talk about I talk about Y given S. Let me go back so that you'll be able to see uh when I was walking you through example on population regression model. Okay. I think I said this. There's a difference between the two, right? One is the average, but the other one depends on the county. And this guy is trying to say, okay, if in 2012, 50% of a particular county voted for a Republican candidate, okay, then you want to figure out what the percentage of votes would be for 2016 for that particular county. So this one, it varies because that goes across our county. But the first one is the average. You've talked about the average. Now, average don't vary, but this one now, this one varies, right? Then we need to talk about the distribution of that. Why do I need to talk about distribution? Okay, so because it varies, then I need a distribution. And that's what we want to do. That's what I want to show you right now. Okay, if you take a look at what I said here, okay, I need a distribution of y given x. You know the meaning of this? Why am I talking about distribution? Because this guy varies. What do you see here? I represent a particular county. Does that make sense? So so this is like why what the Republican candidate got in 2016, given that we know the value they got from a particular county in 2012. Does that make sense? Okay, now we want to stick the distribution for this. Now, this is the distribution now. Please, I needed to pay attention. Okay, y given x equal to that. Follow normal distribution. What is the mean? The mean is beta naught plus beta 1s. What is the variance? The variance is sigma squared. That sigma squared is the variance. If I want to rewrite that now, I'm trying to say expected value of y given x, okay, given x equal to small x, okay, that is beta naught, okay, plus beta 1s, right? Which is the average, which is the population regression model. And that is what you have inside here. When we specify normal distribution, the very first thing is the mean, which is that guy. The second one is the variance. So what we're trying to say now, the variance of VAR is the variance of y given x equal this, okay, is sigma squared. And how do we know it's sigma squared? Because the variance of the error, okay, the variance of the error, okay, we said when errors have equal variance, then y given s is also going to have equal variance. And that equal variance means sigma squared. Does that make sense? That's what we mean. Okay, that is exactly what we mean here. Okay, now because of that, I'm actually going to call that the distribution of y given s. Don't forget, y given s is a random variable because that would depend on the county. We're not talking about average right now. We're talking about what the Republican got in 2016, given a particular percentage they got in 2012 from a particular county. Now, the distribution is going to be normal, okay, with the mean of beta naught plus beta 1x with the variance of sigma squared. And that was why, if I say have conditional independence and they have equal variance. What do we mean by conditional independent? Conditional independent, we mean y given s is independent. The independence of y given s is conditioned on independent of the errors. When errors are independent, then they're going to be independent. And that's why we said they have a conditional independent. Does that make sense? Okay. Now, this is just, okay, you asked about, now this is one of it, okay? Now, when you take a look at what I have right here, where we have y against x, right? Okay, now when the distribution we're talking about, that's a normal, right? Do you see normal? Okay, the center of a normal is the average. And that center here is the expected value of y that we call population regression model, which is for maybe for that 9.5 plus 2.1 s, the beta node is 9.5 and the beta 1 is 2.1. Okay, now this is the distribution when s is 25. Maybe when S is 25, maybe we're trying to say, okay, if 25%, if the Republican candidate received 25% from a candidate in 2012, what we actually are going to get in 2016, if the errors follow normal distribution, then we can actually have that. What about for 45? So take a look at that, okay? Now, I want us to go back into the example. Give me 1 second. I think I'm going to do a cleanup here now. Then before moving forward. Okay, back to our example on the population regression model. You can see we use most of the county in the United States. And of course, we make a projection, when um, the Republican candidate in 2012 got 50% of the vote from a county. So this is on average. Of course, the Republican candidate in 2016, which happens to be President Trump, on average is going to get that. Okay, now the next I want to talk about, if I don't finish this, I'm going to continue in the next class, but I'm going to start this. This is like a different, this is a sampling distribution of least square estimator. Has anybody heard about sampling distribution before in this class? Sampling distribution. Okay, now I'm going to tell you the idea of a sampling distribution, but before